Hello viewers, welcome back. I hope you are doing good. Today we are going to solve another question from line 75 series. This is Leetcode 295, find median from data stream. Since it's a data stream, we'll be getting new numbers every time and there is no fixed set of numbers here, and we can be asked to find the median at any particular instant. First understand what is median. So if we have a sorted list, then whatever is the middle value, that will be the median in that list. For an example, if we have numbers like 1, 2, 3, which are already sorted, median is 2. But let's say I have more numbers 1, 2, 3, and 4. Here there are 4 numbers. So there is no middle value. Instead, what will we are going to do? We are going to take two values, two middle values, and take the mean of 2. That is like 2.5. So 2.5, if you see that is coming somewhere in the middle. So that is going to be the median value in case of even number of numbers. Since numbers are coming continuously, we have to implement a function called add num, which will be taking a new number and keeping it somewhere, and find median, which will be asking us to give the median at that particular instant, whatever number we have. For an example, here you can see that add number is being called with 1, add number is being called with 2, then find median is being called. So initially we have 1, then 2, and if I have to get the median, that will be 1.5 because we will add them and divide it by 2, and then we got another number. So we already have 1 comma 2, and then we got another number 3. Now again I have been asked to find the median, so now median is 2. So you would have understood that the numbers are not fixed, more numbers might be coming in, and find median we can call it at any time. So if I have 5 numbers, I can get a call for find median. If I have 10 number, then again I can get a call for find median. How we can find it? So the one way to one way to store the values is like we can use an array, simple array, and whenever a new value is coming, we can just store the values in that, and whenever a find median calls come, we will just sort the array and return the values. So now let's say we are maintaining a array, and if a new number comes, then we can push that value into this array. Let's say 5 has come, then I'm going to put that in the array, and now I can get request for median. So finding the median, I have to sort this up. Since it was already sorted, number has come in the sorted order, but there might be a case that initially I got number 2, then I got number 1, then I got 3, and now I am getting 5. So 5 will come at the end, and now I can get the request to find the median. In that case, I have to first sort this up. After sorting, my numbers will look like, oh sorry, we have 2. So 1, 2, 3, and 5. Now whatever is the middle value is these two. So the median will be 2.5. So this approach, what is the time complexity? For adding a new number to the list will take us just O of 1 time. So the time complexity for add number would be O of 1. But finding median would be nlogn because we are sorting it. So can we do better? So one way to perform better is, instead of sorting this, whenever we get a call for find median, I can maintain a sorted list. Instead of keeping everything an array, and whenever request comes for median and sort it, we can maintain a sorted list only. So what's gonna happen whenever we get a add num call, I will keep that value in the proper position. What I mean by proper position or the correct position is, let's say I have a number 3 in the list, and now I got a request to add a new number 1. So I will try to find what is the correct place for 1 in this list. I can use binary search and I can easily find out that, okay, the index 0 is the correct position. So now 3 has to shift. So after shifting, 3 will come here and leave its place for 1. I can keep 1 here. Now I can get another number 0. So again, I will perform binary search, and then I have to shift all this number because binary search is telling that the 0 value should go at the first index. Sorry, the 0 index. So 1 will come here and 3 will come here. 0 will go to the first place. So now you can see that we are doing two things. We are shifting the number and we are finding the position, finding the correct position. Finding the correct position cost us log n time because we are performing binary search, and shifting is going to cost us O of n time. So if I have to calculate the time complexity, I can just add them up, and after adding this up, this will come out as O of n because this is the bigger value. So at least we have done better than the previous approach of n log n, but still there is scope for improvement. So now we can draw some observation from our previous approaches that we are always interested in finding the middle values. We are always looking for the middle values. We are not concerned about the sorted order of the other value. The second thing is we want to get the median faster. If we can get it even faster, like we are spending O of n time with the previous approach. If we can do even better, then it would be very nice. So just write the list again and try to think how median we calculate. So median here is the middle value in the odd length number case. And let's say if I have more number, then the median is somewhere here. Median is 4 because if I add 3 and 5, 3 plus 5 by 2 is 4. That is here. So one thing is sure that median divides our list into two halves, two equal halves. In case of even length case, we will get the two equal half, 1 comma 3 and 5 comma 7. In odd length case, we can't get equal halves, but one of the half will be one more than the other half. So now you can see that these medians have divided the list into the two halves. Here the halves are equal, here the halves are not equal. So if I have to take the median, I can easily get these values and find the median. In the left hand side, for finding the median, what I want? I want the largest value. From the right hand side list, I want the smallest value. And 3 and 5, I can just add them and take the mean of that and I can get the median. Here also if we see, since lists are not equal, the list which is having the more value is the median only. So I can just go and take the largest value from the left hand side list and I can get the median. So if in both of the cases, you can see that we are just interested in two things, largest value from the left list and the smallest value from the right list. So what data structure can give me the largest and the smallest values? So max heap can give me the largest value and min heap can give me the smallest value. So if we'll maintain a two list, one using max heap, one using min heap, I can get largest value from the left list and the smallest value from the right list. And if the numbers are odd, then I have to get both the numbers. Sorry, if numbers are even, in that case, I have to find the largest as well as smallest and take the mean of 2. In this case, I can just return the largest from the left list. That would be the median. And here my median is going to be largest plus smallest divided by 2. So now we can maintain a list and we can easily find out the median. So what is the time complexity for finding the median in this case? Heap can give us the largest and smallest value in O of 1 time. But for heap to maintain the values, the largest and the smallest value on the top of its list, it has to spend log n time. It has to spend log n time for each of removal or addition of number. Let's say if new number comes and I have to keep it in left heap. So left heap or whatever heap it has to maintain the heap property. And for that, it needs log n time. So overall, we will be just spending log n time to get the largest and the smallest value, right? I mean, finding the median, because median is not just to get the values. We have to maintain the list as well. Maintaining is going to cost us log n value. Whenever a new number comes, we have to put it into the correct half. The new number can either go to the left half or either it can go to the right half. If the new number which is coming that is greater than the top value of the left half, then it should go to the right half. But if the new number that is coming that is smaller than the smaller value of the right half, then it should go to the left half. So in this case, what we are going to do, we need to compare 8 with 7, the top value of the right side list. This right side list will give me the smallest value. So if the right smallest value itself is smaller than 8, then this belongs to right hand side list, and I am going to put it on the right hand side list and then remove the smaller value from it. And we know that since it's a min heap, it can easily get us the smaller value and then I can put it into the left half. But then this is going to be some work. So instead of checking for values, what we can do is we can directly go and put it into the right hand side list, and then we know that he balance it itself. So it's going to balance itself and 8 will come somewhere after 7. So then we can DQ the value and we can get the minimum value from the right hand side list. After, so first we are going to put 8. So after that, the list might look like this. And then after that, we can remove 7, the smallest value, which we can put into the left hand side list. So we will be doing the two operation. We will be removing, we will be basically encoding the new number in the right list and dequeuing smaller value and putting it back to left list, because smaller value should go to the left list only. So this is like nice approach where we can just blindly keep the value into the opposite list where we should have been ideally putting in, and then take the smaller value from this list and put it back into the left side. So the another case to take care of when the sizes of list are not same. In this case, our left list will be bigger than the right list, and new values whatever is coming we will be tempted to put into the right list because the size is less, but we might violate the value. If I'll put it into the right side list, it will look like 479. Now if you see, we have 135 here, and there is one value 4 here which is smaller than the value here which is 5. So this is not correct. So instead, again in this case, what we could have done is we could have first checked the top value from the left hand side list. The top value is 5, which is more than the new number. So since 5 is more than 4, that means the new value belongs to left list, but we have to put it into the right list to maintain the size. So what we can do? So we can remove the largest value from the left list and put it into the right list. So if we remove the largest value from the left list, it will become like 1, 3, and we can put 5 into the right list. Now we can put the new number into the left list. So instead of comparing with the top value, what we can do is whatever is the obvious half for a value to go in, we can keep that into the opposite half and then take out the minimum or maximum value, whatever it is, and that smaller or larger value based on which half it is, we can put into the opposite half. So what I'm trying to say is 4 should have gone here, but instead of putting it directly here, I can put it in the opposite list. So the opposite list will become like this, which has two more numbers than this. Now remove one number from here. So after removing one number from here, this list will become 134, and then whatever extra number we have removed, we can go and put it into the correct half. So instead of directly putting into the obvious half, we can put it into the opposite half, then remove something from the opposite half and then put it into the obvious half where we wanted to put the value. So I hope that you have understood the algorithm behind this. Now we'll try to code this up. So I'm going to create a max heap for the left portion. So new of heap, and since it's a max heap, so I'll pass a comparator function where I want the values in ascending descending order. So it will be b minus a. Then I want a min heap for the right portion. In min heap, we no need to pass anything because that's a default implementation. Since we know that in JavaScript we don't have an internal heap implementation, so we'll go and take our custom implemented code and use it here. I have a separate video on that. You can go and refer that. The code link will be in the description. So now I have both the heaps created. So the cases to enter the values would be, in first case, both the size would be same, what we discussed. When the size of both the lists are same, the obvious thing for a new number to go into the left hand side list, but instead of putting that into the left hand side list, we'll try to put it into the opposite list. So that's why we will put it into the right heap. So now after putting the value into the opposite heap where I should not be putting in, I would have created one more value to that heap. So let's remove that. So we'll just copy this up, and instead of dq, we are going to do, sorry, instead of inq, we are going to do dq. So now I've removed this value, and this removed value should go into the left half because ideally everything should have been left half, but to maintain the value property, we have kept it into the opposite half. I've already explained this. So when the sizes were same, rather than putting it to the left half directly, we are putting it to the opposite half, and now opposite half has more values. So we have removed one value, which will be the smallest value because this is the right half, so smallest value, and now I'm putting the smallest value into the left half. Now on the else case, the sizes are not same. That means the left hand side list is bigger. Left hand side list is bigger than the right hand side list. Now if the new value comes, so ideally we should be putting it into the right hand side list. That's the obvious way. But instead of putting that into the right list, we'll put the value into the left list, the opposite half. And now since I have put the value into the opposite half, let's say here I put the new value which is 6. So now we have more characters or more elements here. So I need to remove the values. So I'll just copy this up and I'll dequeue the right half. Sorry, I'll dequeue the left half because it has more values now. So taking a one value from the left half, I'll be getting the biggest value from the left half, right? The largest value from the left half. I can put I can put that up into the right half. So I'll go and put this into the right half. And I think I missed writing NQ here as well. So again, to reiterate what we are doing, instead of putting it into the obvious right half, I'm putting it into the opposite half. Now opposite half has one more value. So I've removed the one more value from that half, and that should go into the correct right half now. Same whatever we are doing here, we are doing exactly opposite. Now at last, the median value. So if size is not same, that means we have more value into the right list. Something like this. We have more value into the right list. So it's a odd case. In that case, the top value of the left heap will give me the median. So if size is not same, then I can just go return the peak of left heap. But if that's not the case, then it's a even number values. In that case, I am going to take the peak from both the list. So let's add them up. And then take the mean of that. So let's run it and see if it works. As you can see that this is working for the sample test cases. Let's submit and see if it is working for all of the test cases. So looks like this is working for all of the test cases. I hope that you have understood the solution well. It was little difficult for me to explain it because this solution is not that easy. In this approach, whatever we have done, taking the heap and divide it into the two halves, this is not very intuitive to come up with, but that's fine. I try to do it yourself. You will get the more understanding out of this. So if you have liked the video, please hit the like button and subscribe to my channel. There will be more videos coming in. Keep watching. See you in the next video.